Alrighty, lads and ladies, welcome back to Calc 2. Unfortunately, last week we were cut short in our discussion of infinite series by UF's Homecoming. So we're going to play with that. Yeah, the beard's gone. I know. It feels weird for me too, but I have an infant son, and as he gets stronger and stronger and stronger, his ability to pull hard on that beard got a little rough. So I apologize for the shock. I promise it's the same dude. And today we're going to continue talking about the same stuff. So first, a word or two about your tests. The tests are graded. And in fact, let me take an extra second to talk about this because it really warrants it. And there's something I want to show you. So I don't know how to say this. The grades on the tests were poor. Like quite poor. Probably the lowest scoring test I've seen in Calc 2, at least in recent memory. I haven't actually looked back at the stats. But there's problems there, there's real issues. And I don't curve. It's just not something I do. I don't believe in curves as a general rule, and I will be considering some grade adjustment here because the average, if I'm not mistaken, it was in the low 40s, which is bad. About 20 points lower than I usually like to see an average on a test like this. So a few comments here, and I'm not saying any of this to make you feel bad. I'm just trying to effectively communicate. This test is very similar to tests I've used in the past. It's, some of you are retaking this class with me and are aware, no doubt, that this test is certainly not identical to, does not have the same answers, and some of the problem types are a little bit different, but is very similar to the exam one that I've used for the last year or so. I modified just enough so that somebody who's seen the test before can't guess at the answers on any one. So I'm saying that to say that this is not an especially hard test. It really is not. In fact, it's a good deal easier than the tests I used to offer when I taught this class in person. But the scores here are much lower. And on the one hand, I am grateful for one of the things that indicates. That indicates that probably there's a lot less cheating going on. I know that there has been in the past, because I've caught so goddamn many, there has been a lot of cheating over the last year or so. So I am grateful that you guys showed me your honest skills, and I don't want to punish that. So that's why I'm looking into some sort of grade correction. On the other hand, it shows me that we're largely not ready for the level of work that's expected in this class. And I realize that can be for a number of different reasons. So the first and most obvious being that, just like I've had to deal with a lot of cheating in Calc 2 over the last few semesters, a lot of people have come through the prerequisite classes for this class without necessarily developing the skills that one would think they have based on the grades and the transcript. And I'm saying that as gently as I can. I'm not saying everybody cheated their way here. I know that's not true. I know a lot of you, probably most of you, worked very hard and very honestly to get through pre-calc, trig, and calc 1. But I also know that even the strongest and bravest and most honest of us from time to time lapse in judgment, and that those lapses in judgment have consequences, which perhaps have slightly come home to roost here. So here's what I want to say. First, the statistics. Sorry, one second. Okay, here we go. So the stats. Here they are. Yeah, the average was 45. Our high was an 85. Our low was a 6, and I think we had 2 of those. This is worrying. I know many of us probably haven't taken statistics, but a standard deviation is kind of a measure of spread. And this down here is a histogram of the scores. Usually what we see is a cluster of scores around here, and then another cluster of scores around here. And the way I've interpreted that in the past is like, okay, here's a group of people that had the necessary background skills and studied, you know, and then where you fall in that first cluster between like 70 and 90 usually depends on how much time you put into practicing problems. And then the second cluster, either, you know, we didn't have enough time to study, or we have some issues with Calc 1 or algebra stuff that's causing us some trouble. Trigonometry is often a source of that second thing. And all of that is okay, but you see here this distribution it's closer to a uniform distribution than it is any sort of normal or bimodal distribution, which means that for a bunch of reasons, our skill set is all over the place, all over the place. And there's a lot more entries down here south of 50 than I would like to see. And there are reasons, of course, for some of these, you know, and I acknowledge that, right? Sometimes life just fucks you really hard and you look at the test and you go, I don't have a fucking clue what to do. You Christmas tree, the true, false, and multiple choice, leave everything else blank. And that happens. It does. We've all had experiences like that. We need to tighten up, right? We need to tighten up big time. So I want to share with you something that I actually saw this morning on Reddit. R Math on Reddit, I'm sure you guys all know what Reddit is. R Math on Reddit is a great subreddit. It's a cool place. Used to be mostly mathematics researchers talking about math research, but it's become a much broader thing now where everybody talks about all sorts of different math things. And I saw this post this morning while trying to think about what I should say to you guys. And mathematics is not a spectator sport. That sounds obvious, but it's not. So I'm going to link this in the chat. I'd like you all to read it. Not just the OP, but please also the comments. I know it sounds silly to have a math professor telling you to read Reddit, but there it is. This particular person is a Calc 2 student, and they were able to sail through their previous classes with a minimal amount of effort, you know, watching the lectures and then working just the problems that were required, got them through Trig, Pre-Calc, Calc 1. And then they arrived at Calc 2 and it didn't work anymore. And I think maybe a lot of us are experiencing that now. So the upshot here is this quote from Paul Halmush that mathematics is not a spectator sport. You cannot learn to do this shit by watching me do this shit, no matter how well I do it. No matter how clearly I explain or how many examples we look at, watching me or anybody else, you know, Professor Leonard, take your pick, Patrick JMT, will not get the job done. There's one thing and one thing only which will get the job done. And you'll see in this post as you read it, that the thing is problem solving. Honest, independent problem solving, where you work by yourself on problems until you are fucking good at them. And you must do that. It's necessary. It's the only way. I understand that it might not have been the way you got through your previous math classes, but as you approach the edge of your skills, right, not the edge of your ability, because you'll find that your ability changes all the fucking time. The more you practice, your ability will change. Knowledge and intelligence are not fixed things. They change when you practice. But as you approach the edge of your skills, you will find that you need to grind to improve them. If you've ever tried something like hula hooping or programming or playing competitive video games or skateboarding is a great example, right? I remember spending probably 15 hours learning how to ollie on a skateboard when I was like 10 years old. It didn't come right away. And no matter how much Tony Hawk Pro Skater you play, or no matter how many skate videos you watch, you're not going to get good at it until you stand out there and grind. And there's going to be a lot of falling over. There's going to be a lot of getting it wrong. And you need to not be discouraged. You need to continue the grind until you start getting it right, until you start getting it right every time. And once you have that, it's going to be this amazing feeling. And you're going to feel so empowered moving forwards. this individual talks a lot about their emotional responses to not so great grades, and especially a few of the comments down here. So there was one here that I liked a lot that I want to share. This one. So the OP is talking about how they discovered once they put in an honest grind, things started to turn around, meaning like working 50, 60 problem sets on their own until they get it right. This person says, I'd like to offer myself as an example that you can perfectly well get by with doing mostly spectating the way you did in high school, right? Just watching, not really grinding and practicing. I mean, why make all the exercises when you can just wing it on the exam? You don't even need to go to all the lectures. Just go into a stress and ADHD infused cramming session the week before. If you go for this method, I can assure you that while those other pesky students will only spend some 3 years on their bachelor's degree, you'll get the full ride and experience everything there is to experience. Failure, existential doubt, promises that next semester you'll do better, more failed classes, and a beautiful 10-year bachelor degree experience, which means you're over 3 times as good as Mr. I actually showed up for class and did all the exercises. Obviously, he's being sarcastic, or she. So all of this is to say, the test grades were poor, and they may stay poor. I'm going to talk to some of my colleagues and see how we feel about the possibility of something like a curve. I'm deeply allergic to the idea of a curve. It goes against everything I believe in philosophically as a teacher and a learner and expositor of mathematics. But I don't want to penalize you for being honest, and I'm grateful that you as a class were quite honest with your skills, and that's good. That's what we want to see. On the other hand, you must learn to change the attitude. You need to approach this in a different way, and I'm speaking really to pretty much everyone here. There were some okay and good scores on the test, but all of us can improve. And if you did anything other than work large volumes of problems on your own until you got them right and felt good about them, then you need to change how you approach this. Remember that first part of the class, the stuff that we tested on exam 1, that's the easy part. The stuff we're doing now is harder. It's more logic-based. The algebra steps are at least as challenging. The notation and concepts are way heavier. So if you're not happy with the score you got on exam 1, it doesn't mean you're a bad person. It doesn't mean you're a bad student. It doesn't mean anything like that. It just means what you were doing isn't working. And you don't need to take that as something to be upset or sad about, but you do need to take it as an indication that something needs to change. I want to help you. I want to help you in every way I can. And to that end, you've got lots and lots of stuff in the modules there. Paul's online notes has tons of practice exercises you can work. And of course, there's the textbook. And I'm happy to get you guys a copy of the text if you don't have a copy that you can easily leaf through and solve problems. But you must do that, right? You must. I strongly recommend every section we go through, in addition to the homework problems on WebAssign, which in many ways, let's be honest, are bullshit, go into the textbook and solve problems. Solve them until you're getting them right the first time. You can check your answers with things like Wolfram Alpha or Mathway or Symbolab or whatever, but if you use those tools to get through the homework and then you don't practice additionally, the test is not going to go well. And it's very easy to fool yourself into thinking that you've got this when really something is holding your hand through the practice sessions. So please work hard to be independent learners. Because that's what we all are. We can get help. There's nothing wrong with getting help. But after you get that help, you need to reinforce. You need to go in and actually make sure you've learned it. You need to do the grind that's being discussed in this Reddit post. So that's my spiel. I'm going to get down off my soapbox now. Those are the facts, right? So the average was 45. That's bad. That's bad. And there are reasons, understandable and acceptable reasons why someone would do bad on a test. And it's not something that you should feel personally bad about, but you should take it as a clear sign that something needs to change. And I want to help you change that thing, whatever it is. And you can talk to me if there's stuff going on in your personal life, if there's stuff going on in your work life, if there's stuff going on elsewhere at school or whatever it is. Especially if there's like a hole in your background. You're like, every time I see this thing, I get nervous. I don't know what to do, or I make a mistake and then I feel shitty and I give up or whatever. Talk to me about that stuff, please. Big part of my job is not just like spewing mathematics at you, but it's also kind of helping you overcome those challenges. Little story, I haven't told you this, I told my pre-calc students and then I'll stop. I failed algebra 1, not once, not twice, but 3 times in high school, right? In middle school and then twice in high school. And then in college, I failed college algebra, I think 3 or 4 times. My mom was a professor at the community college where I went to school. And so I didn't stay in the class, I withdrew, and then I ended up, because I failed it so many times, I had to do, like Santa Fe has that 3rd attempt thing, right, where they get on your ass after you fail a few times or withdraw a few times. I had to get like special permission to continue going to school. I know what it's like to have that feeling of like, I'm so fucked, like everything sucks. And I know how hard it is to get that momentum back up where you're studying and feeling good. When you feel bad about where you are, it's really, really hard to sit down and have a productive study session. And I understand that. So I think our first step is to get you feeling good again. And then we can have those good study sessions where productive things happen. And the best way to get you feeling good is to solve problems and get them right. And if that means we got to go back to trig, I can get you some trig problems. That means we got to go back to function notation, dealing with radicals, exponents, graphing, whatever it is. Let's go back there and do that. Let's get you feeling good again so that you can have those good study sessions and make forward progress, because that's what I want for you. Okay, that's it. Enough rambling. Let's talk about some mathematics. Last time, so this is MAC2312, section 004. That means it's Calc 2. And today is the 11th of October, 2021. Last time we learned what an infinite series is. So I'll remind you that definition. Oh, yeah, sure. Here, I'll go ahead and throw this into the Discord. There we go. Okay. Last time we defined what an infinite series is. I want to pick it back up there. I'll remind you the definition. We'll start working some more examples. I am going to extend that homework set because we didn't get to talk on Friday. So recall. Obviously, today we're talking more about infinite series. Recall. Given a sequence an, so like 1 over n, or a sine of n, or whatever, given a sequence an, one can form a series by adding up all the terms of that sequence. And what that series looks like, I'll call it S, capital S. That would be sigma n from somewhere. We call it 0 or 1, doesn't really matter. Somewhere to infinity of an. So remember what this capital sigma notation means. It means you're going to add this thing up as n goes from 0 to infinity. It's like an integral. It's like a type 1 improper integral. This is just a shorthand for the infinite sum, a0 plus a1 plus a2 plus a3 plus a4. It goes on and on and on forever. As the limit, and we introduce a new variable here, capital N, which is like capital R from your type 1 improper integrals, limit capital N to infinity, sum from little n equals 0 to capital N of a sub little n. The finite sum from little n equals 0 to capital N of a little n is called the capital Nth partial sum of the series S. And is denoted S sub capital N. All right. So all together, what that means is that the big, scary, infinite sum is equal to the limit as capital N goes to infinity of the much less scary finite sum out to capital N. And often we write this as, so the full series we call S, and often we write this finite sum here. So I've got my lim capital N to infinity still as S sub capital N. And I mentioned this on Wednesday of last week. Your book kind of fucks up in that they use the same variable. They use a little n when they talk about the nth partial sum. I really don't like that. I think that's bad notation because little n is also the index of summation. All right, so this is our definition of an infinite series. The other thing we want to define is what it means for an infinite series to converge. The infinite series S is said to converge if the limit that defines it, lim n to infinity of S sub n, capital N, exists and is finite, i.e., and this is where people get a little bit confused, the sequence S sub capital N is a convergent sequence. If the limit of the partial sums diverges, if this limit does not exist, if then capital N to infinity S sub capital N is infinite or does not exist, then we say that the full series S diverges. Okay, so I want to talk for a second about the notation. You notice there's a shitload of words and notation here. Take a second, make sure you have this written word for word correctly in your notes. S, remember, is the full infinite sum. Sn is the partial sum. So the difference between S and Sn, Sn stops at capital N, S goes all the way up to infinity. The series S has infinitely many terms in it. The partial sum Sn has finitely many terms in it. And the way we handle this sort of thing is the same way you handle a type 1 improper integral. The sum all the way up to infinity is the limit of the sum up to capital N. Just like the integral from 0 to infinity is the limit as r goes to infinity of the integral from 0 to r. The analogy runs really deeply. At this stage in our understanding, the big thing is to see the difference between the partial sum, the full sum, and the sequence an. So the first place people run into trouble here is thinking that A little n and S big N are somehow the same thing. They very much are not. Very much are not. The second place people run into trouble is with the sigma notation itself. This sigma notation here, sigma n from 0 to infinity, is not a limit. It's not a limit. You cannot replace it with a limit. You can replace the sum from 0 to infinity with a limit and a sum from 0 to n. That is symbolically true and reasonable. But the sigma on its own is not a limit. It's an operator telling you to add some stuff up. So before we get into any theorems or full results, I want to just look at a few very simple examples, and I want to make sure you understand partial sums all the way. Because this is the part of the class where people kind of fall off the wagon, I want to take the time here in 11.2 to completely understand this in hopes that it'll give you something to hold on to through 11.10, because we're going to do a lot of this stuff. I'll tell you now, and people who've taken classes like this with me in the past can verify this, that I will sacrifice other parts of the class to make sure that this gets through. Meaning if we have to cut short some shit later in the semester to make sure you really understand series, we will. Before I start looking at examples where we play with these objects individually and together, are there any questions about what's being defined, the terminology, what sort of animal any of these things are, anything like that? Any part of this that we feel uncomfortable with, just sort of on its face? All right, examples. I'm going to be using some computation tools here, some calculation tools, because the arithmetic itself can get a little bit out of hand. Let's start very simple. We're going to compute the first 5 partial sums for the following series. Sigma n from 0 to infinity of 1. Sigma n from 0 to infinity of -1 to the n. Sigma n from 1 to infinity of 1 over n. We're going to do some more. Sigma n from 1 to infinity 1 over n squared. And sigma n from 0 to infinity 1 over 2 to the n. Each of these objects is an infinite series. Right? These are the main things that we're trying to wrap our head around in section 11.2 and 11.3. And while we will go on to develop many tools for these things, you'll be able to tell me in the blink of an eye next week whether each one of these converges or diverges, and in some cases you'll be able to tell me what they converge to. Even if you have some a priori knowledge about that, we're going to approach it right now from this naive perspective of the definition of an infinite series. And what that means is we're going to look at the partial sums. Each infinite series is the limit of the partial sum. Okay. All right. S sub n here, my nth partial sum, would be the sum from n equals 0 to capital N of 1. And I think it's worth taking a second to just look at what this means. This is 1 plus 1 plus 1. Remember what the sigma says. Sigma says add this thing up as n runs from 0 to capital N. So this first guy is the little n equals 0 term. The second guy is the little n equals 1 term. This next guy is the little n equals 2 terms. The thing in the sum doesn't depend on little n. It doesn't have any little n's in it. So when n is 0, this is 1. When n is 1, this is 1. When n is 2, this is 1. No matter what little n is, the thing we're adding up is always 1. The next term would be 1, and so on. It's always 1. So this is little n equals 3 term. This is the little n equals capital N term. So just remembering what the sigma notation means and remembering the definition of the nth partial sum. Just for fun here, what is a sub little n? What is the sequence that's being added up? Look back at that definition page. What part of this apparatus is a little n? Don't overthink it.
1.
Yeah. Is a constant sequence. So just like you integrate a constant function, here we are summing a constant sequence. Okay, we want the first 5 partial sums. Since this series starts at 0, the smallest number I could possibly plug in for capital N is 0. So S0 would be the sum from little n equals 0 to 0 of 1. If I were to write this out in this form, what would I get? One minute there. All right, sorry, the dog's being crazy. All right, so yeah, how many of these terms are we going to have here? What is the sum from n equals 0 to 0 of 1? I see some stuff in the chat. It's 1. Yep, I wouldn't think of it as n to the 0 though. It's just like this term, right? This is the n equals 0 term. It's just 1. I think as we look at more of these, it'll become a little easier. S sub 1 would be the sum from little n equals 0 to 1 of 1. So that's going to be the first 2 terms. 1 plus 1, which is 2. S3 would be the sum from little n equals 0 to 3. Sorry, I skipped over 2, didn't I? S2, sum from little n equals 0 to 2 of 1. This would be 1 plus 1 plus 1, right? This is the n equals 0 term. This is the n equals 1 term. This is the n equals 2 term. So 1 plus 1 plus 1 is 3. S sub 3 is the sum from n equals 0 to 3 of the constant sequence 1. That's going to be 4 terms there altogether. 1 plus 1 plus 1 plus 1, right? When n equals 0, a0 is 1. When n equals 1, a1 is 1. a2 is 1, a3 is 1. So this is 4. So the first 5 partial sums here are easy to compute. This last guy, S4, would be the sum from little n equals 0 to 4, which is 1 plus 1 plus 1. Alrighty, there we are. So these are the first few partial sums for this, for this infinite series. All right. S0 was 1, S1 was 2, S2 is 3, S3 is 4, S4 is 5. What this series is doing is just adding up 1 plus 1 plus 1 plus 1 plus 1 infinitely many times. And what Sn does is it adds up 1 plus 1 plus 1 plus 1 finitely many times. So what we see here, we can actually write down a nice formula for Sn. S0 is 1, S1 is 2, S2 is 3, S3 is 4. S sub capital N is capital N plus 1. So here, S, the full infinite series, which remember is the sum n from 0 to infinity of 1, by definition is the limit as capital N goes to infinity of S capital N, which would be the limit as capital N goes to infinity of capital N plus 1. And yeah, as capital N goes to infinity, as we go further and further and further out here, these numbers are just getting bigger and bigger. This would be infinity. So this is a divergent infinite series. And what you'll see is it's actually quite rare that we can conclude much working directly with the partial sums, but in these very simple cases, we can. And I think it's similarly easy to see that if this was any constant, right, here an equals 1 is what constant sequence. If an was the constant sequence 2 or 5 or pi or 10, you'd just be adding 2 or 5 or pi or 10 to itself infinitely many times. So those would all be divergent. All of those partial sums would be very easy to compute and find the same pattern, and you could deduce that the full series diverges. This is the easiest of all possible examples. Let's look at part B. All right, the full series S is sigma n from 0 to infinity, -1 to the n. So the nth partial sum, S sub capital N, is sum from little n equals 0 to big N of -1 to the little n. So my sequence that I'm adding up here an is -1 to the n. It's not a constant sequence, but it is bounded. It doesn't, the terms don't get big. It's a kind of, not super interesting sequence. But when you form a series out of it, you get something new, which might be interesting. Okay. S sub 0, the kind of earliest partial sum I could talk about, would be sigma n from 0 to 0 of -1 to the n. That's a series with one term. That's just -1 to the 0, which is 1. S sub 1, the series from little n equals 0 to 1 of -1 to the n. That means I'm going to plug in 0 here and then add that to what I get when I plug in 1 here. Right? So this would be -1 to the 0 plus -1 to the 1, which is 1 plus -1, which is 0. The next partial sum would be S sub 2. Capital N here is 2. is the sum from little n equals 0 to 2 of -1 to the little n. So that means I'm going to add up this thing as n runs from 0 to 2. So that means I've got my -1 to the 0 plus -1 to the 1 plus -1 to the 2. And then I can compute this. -1 to the 0 is 1. -1 to the 1 is -1. So I'm going to write that as -1. -1 to the 2 is +1. So this is 0 plus 1 is 1. And we'll start to see a pattern. Just pretty quickly, S3 would be the sum from little n equals 0 to 3 of -1 to the little n. Okay, so the big step here is going from here to here. Right, from here to here. Simplifying that is easy for all of these. So this would be -1 to the 0 plus -1 to the 1 plus -1 to the 2 plus -1 to the 3, which is 1 minus 1 plus 1 minus 1, which is 0. And I bet you see the pattern at this point. 1, 0, 1, 0. S4 is going to be what?
One.
Yeah, it's going to be 1, right? Because it's -1 to the 0 plus -1 to the 1 plus -1 to the 2 plus -1 to the 3 plus -1 to the 4. It's the same as the previous thing, just with one more term. And that one more term is a +1. So this is 1 minus 1 plus 1 minus 1 plus 1, which is 1. And in general, the nth partial sum, there's no nice algebra formula for this, but I can kind of describe it piecewise. It's 1 if capital N is even, and 0 if capital N is odd. So what can we say about the limit of the SNs? So remember S, the full infinite series S is always the limit of the capital Nth partial sum. What can we say about the limit of this guy? Yeah, if you look at the graph of Sn, this is the place I think people get into trouble, because An is a sequence, S is a series, and the series S we understand by looking at another sequence called Sn. There's a lot of back and forth there. So the sequence Sn has a graph looking like this. I'll mark off 1, 2, 3, 4. It goes 1, 0, 1, 0, 1. So those dots are not getting closer and closer to anything. This limit does not exist. So we'd say that the series S diverges. Don't confuse Sn with An. They're not the same. Don't confuse Sn with An. They're very, very different. Sn is what you get by adding up the first n terms of the sequence An. They are related, but not the same. Later, we will have theorems connecting them, but for now, we just want to get comfy with the notation and the definition. So are there any questions at all about these computations? Everybody's 100% comfy. If not, I want to know, what are you thinking? Where are we worried? This is the time to fix that stuff. All right, remember, we're trying to wrap our head around S infinity, right? S, the full infinite series S, is basically S sub infinity. And here, since the SNs just go 1, 0, 1, 0, 1, 0, S infinity doesn't exist, right? In the same way that the limit as x goes to infinity of sine pi x does not exist. This next one is quite famous, and here's the first place I'm going to use lean on some help, probably, some calculator help. Part C, S, so let's see. The full infinite sum here is the sum from little n equals 1 to infinity of 1 over n. I can't start this one at 0 because if I tried to start this at little n equals 0, my first term would be 1 over 0, which is undefined. So the nth partial sum here is the sum from little n equals 1 to capital N of 1 over little n. And here, the ANs, the sequence being added up is 1 over n. That sequence has a name, it's called the harmonic sequence. And this series has a name, it's called the harmonic series. It's a well-known series, we'll talk more about it later. Let's just look at the partial sums. The first partial sum I can talk about is S1, because my series starts at 1. And that would be the sum from little n equals 1 to 1 of 1 over little n. That's a series with one, it's got one term, it's 1 over 1, which is 1. S2 would be the sum from little n equals 1 to 2 of 1 over little n, which is 1 over 1 plus 1 over 2, which is 3 over 2, or 1.5. S3 is the sum from little n equals 1 to 3 of 1 over little n, which is 1 over 1 plus 1 over 2 plus 1 over 3. And what is this? Let's see, so that is 9, 10, 10 thirds? No. Okay. So this is what I meant, my arithmetic gets slow. Let's use so generate nicer numbers. So what is this? 11/6. S4. Of course, you can take you just have to have a common denominator, right? It just takes some time. S4 is the sum from 1 to 4 of 1 over n, which is 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4. And if I want that as a nice simplified fraction, again, the big step is here to here. This is what I want you guys to be understanding right now. And then if I want that, I can just add 1/4, 25/12. So Desmos is doing the common denominator and simplification of the fraction for me. One more. S5 would be sigma little n from 1 to 5 of 1 over n. So here that's 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5. And if I ask Desmos to add 1/5 to that, I get 137 over 60. All right, now a really rough approximation here. 1 is, of course, 1. 3/2 is 1.5. 11 over 6, pretty close to 2. 25 over 12, also pretty close to 2. 137 over 60 is like a little bigger than, it's like 2.3, something like that. What was it? Exactly. Yeah, 2.28, 2.3, close enough. Here, we're not going to find a nice formula for Sn. So right now, I don't know if the full series S, and maybe this time I'll write it out, which is 1 plus 1/2 plus 1/3 plus 1/4, on and on forever, which is the thing that we're playing with, sigma n from 1 to infinity, 1 over n, converges or diverges. Those first few examples were so easy that we got a nice formula for Sn. In general, we're not going to find that. In general, it's going to be very hard to find. But if you look at the trend here, 1, 1.5, 2, 2, 2.3, these are getting bigger, right? They're getting bigger. So we might think it diverges, but it depends on how fast they're getting bigger. Maybe they kind of approach some number just in an increasing way. Hard to say. Hard to say. Okay, how am I doing on time? 10:25. Got enough time to do the last two. And I am going to give you a result on geometric series. So 1 over n squared next. Sigma 1 over n squared. Focus, focus. Okay. Here, S, the full infinite series, is sigma n from 1 to infinity, 1 over n squared. So Sn, my nth partial sum, is the sum from little n equals 1 to big N of 1 over n squared. And here, An is 1 over n squared. Sn is going to be quite complicated, just like it was for the last one. But we're going to write out the first few terms and see if we notice any sort of patterns. S1, sigma little n from 1 to 1 of 1 over n squared is 1 over 1 squared, which is still 1. S2 is sigma little n from 1 to 2, 1 over n squared, which is 1 over 1 squared plus 1 over 2 squared, or 1 plus 1/4, which is 5/4. S3 is sigma n from 1 to 3 of 1 over n squared. So expanding that out, that's 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared, which is 1 plus 1/4 plus 1/9. And here's where I'll start in this duodecimos again. So I get 49/36. S4 would be the sum from 1 to 4 of 1 over n squared, which is, I'm not going to write this part, I'll just go straight to this part, right, which is 1 plus 1/4 plus 1/9 plus the next guy, 1 over 4 squared, is 1/16. So 205 over 144. And then we have one more to do. S5 is sigma little n from 1 to 5, 1 over n squared, which is 1 plus 1/4 plus 1/9 plus 1/16 plus 1/25. It's true, yeah. For the last problem, we do not know. So part C, at this stage, we do not know if that series converges or diverges. We wrote down the first 5 partial sums. We noticed that they're increasing, but we can't say whether they're going to increase to infinity or increase to some finite limit. It's hard to say. And specifically, we weren't able to find a nice formula for Sn. That was the thing. So this last guy, 5,269 over 3,600. 5,269 over 3,600. And we can look at the sizes of these. 1.4 is about 1.5. 205 over 144, about 1.4 also. About 1.36. 5/4 is 1.25. And of course, 1 is 1. So here, this, if I gave you the first few terms of a sequence, I told you they're 1, 1.25, 1.36, 1.4, and that last guy, let me give you a little more precision, 1.46. These look like they might be getting closer and closer and closer to something, right? These are numbers that appear to be piling up. Now, the value of this series, let me hold to the pattern we were doing here before. I don't see a nice pattern in these partial sums. So again, very hard to find a formula, find a nice formula for Sn. But as big N gets bigger and bigger, the values of Sn appear to be getting closer and closer, approaching some number. Let me look at one more term, and I'm just going to do it in Desmos, right? If I add the next term, 6 squared is 36. So 1.49 would be next, right? Some number in the neighborhood of 1.5. Does anybody know the full value of the series? So, surprising fact. It turns out many of these infinite series, not just like we don't know them yet, but like nobody knows them. But a surprising fact, this series does converge, although we don't know it yet. And the value of the full series. Do I have any Riemann enthusiasts? Does anybody know what this is? Euler enthusiasts? This was called the Basel problem. There's a lot of numbers that are kind of close to 1.5. The version of that we're looking at turns out to be pi squared over 6. But that's way beyond the scope of that class. Yeah, turns out it's about 1.64. If you give yourself more and more terms, 6 squared, 7 squared, 8 squared. You see, we're getting there. We're getting there. Although we will not be able to prove this, we will be able to prove that it converges, that this series converges, but not today. But you see the pattern, right? These numbers are like getting closer and closer to something. They're not just running away to infinity. They're not just getting bigger and bigger. This last example is probably the most important. Let's see, I have you guys from 9:30 to 10:45, right? Yeah. So our last example where we're working with partial sums today is this, and then I'm going to prove a general theorem about series of this type. So in part E here, we're looking at sigma 1 over 2 to the n. So the full infinite series. This one goes back to starting at 0, 0 to infinity, 1 over 2 to the little n. So the nth partial sum is sigma n from 0 to capital N, 1 over 2 to the little n. And here, an is 1 over 2 to the n. What kind of sequence is a little n? Like the first example was a constant sequence. What kind of sequence is 1 over 2 to the n? It's one of the special sequences we talked about last week. It's a geometric sequence. And for that reason, this series would be called a geometric series. So if you form a series out of a geometric sequence, if you add up all the terms of a geometric sequence, we call those geometric series. And I'll prove the full result for these, but you're going to like this one. This one's going to be nice. S0 would be the sum from little n equals 0 to 0 of 1 over 2 to the n, which is just 1 over 2 to the 0, which is 1, because 2 to the 0 is 1. S1 is the sum from n equals 0 to 1 of 1 over 2 to the little n, which is 1 over 2 to the 0 plus 1 over 2 to the 1. That's 1 plus 1/2, which is 3/2. S2 would be the sum from little n equals 0 to 2 of 1 over 2 to the little n, which is 1 over 2 to the 0 plus 1 over 2 to the 1 plus 1 over 2 to the 2, or 1 plus 1/2 plus 1/4. Which is going to be, let's see, I think 7/8. Yeah. No, sorry. 5/4 maybe. Let me just, we'll put this in here. Need it anyway. That's where we are. Yeah. And fraction form 7/4. Right the first time. 7/4. S3 is the sum from little n equals 0 to 3 of 1 over 2 to the little n. And I'm just going to start writing it like this. That's 1 plus 1/2 plus 1/4 plus 1/8. Which is 15/8. And we'll do one more. S4 would be the sum from little n equals 0 to 4 of 1 over 2 to the little n, which would be 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16. And just to really drive home, again, this is the little n equals 0 term. This is the little n equals 1 term. This is the little n equals 2 term. This is the little n equals 3 term. And this is the little n equals 4 term. And we're adding them up. Looking at the last few, without doing the computation, 1, 3 over 2, 7 over 4, 15 over 8. What is the denominator here going to be? The denominator so far, 1, 2, 4, 8. What's the next denominator?
16.
16, very good. What is the numerator going to be? 1, 3, 7, 15. Oh, I heard it. What was that?
31.
Yeah. And how are we finding those? This is 1 less than 2 squared. This is 1 less than 2 cubed, right? 2 cubed is 8. This is 1 less than 2 to the 4. 2 to the 4 is 16. So this should be 1 less than 2 to the 5. 2 to the 5 is 32. So 31 is correct. And we can verify. Boom. So we do have this pattern nailed down. The nth partial sum, let's see, appears to have denominator 2 to the capital N. That makes sense because that's the largest thing downstairs. And upstairs is the next power of 2 minus 1. Whoop, sorry. 2 to the N plus 1 minus 1. Does anyone know how to take the limit of this? So again, remember, if you have a nice formula for the nth partial sum, the full series is the limit as capital N goes to infinity of those nth partial sums. So here, I can say, okay, this is the limit as n goes to infinity of 2 to the n plus 1 minus 1 over 2 to the n. Does anybody have an idea for how I could try to take this limit? Yeah, we can divide top and, well, so here there aren't any powers of n. So suggestion in a DM was divide top and bottom by the largest power of n. Unfortunately here, n is the power, right? But I could divide by the largest power of 2, I think, and that would work. If I divide top and bottom by 2 to the n or 2 to the n plus 1, that would work. I think in this case, though, the algebra is such that there's a nicer way. I can split up the fraction as 2 to the n plus 1 over 2 to the n minus 1 over 2 to the n. All right, fractions can be split up across their numerators like this. What is the first piece there? 2 to the n plus 1 divided by 2 to the n. Forget about the limit, just simplify. How does this simplify? Yeah, it's 2 to the 1, right? You subtract the powers. So 2 to the n plus 1 divided by 2 to the n is 2 to the n plus 1 minus n, which is 2. So you have 2 minus 1 over 2 to the n. And as n goes to infinity, 1 over 2 to the n goes to 0. So this is 2. And this is the origins of one of the worst math jokes of all time, which I'll share with you now. An infinite number of mathematicians walk into a bar. The first guy orders 1 beer. The second guy orders a half of a beer. The third guy orders a fourth of a beer, and so on. The bartender says, "Fuck, I hate you guys," and pours 2 beers. That's it. That's the joke. It's bad, I know. All right. Here's the theorem on geometric series. And then I will let you go. I'm just going to state it. We can discuss the proof a little bit next time. We have the skills to prove the theorem, but I'm not sure that it has ever really helped a Calc 2 student to see the proof, at least right out of the gate. So I'm going to show it to you and give you some time to digest it. Yes, that's correct. Yeah. So that's the theorem that I'm discussing here. So, this is our first and perhaps most important theorem on the convergence of infinite series. And you're supposed to have seen this in pre-calc, but not everybody does. So a geometric series S is one in which AN, the thing being added up, the sequence being added up, is a geometric sequence. Something like AN equals A times R to the N. Remember, that's what geometric sequences are. S equals sigma n from, I'm going to say 0 to infinity, A times R to the N, geometric series, converge if and only if the absolute value of R is less than 1. And in that case, I'll say, and diverge otherwise. If the absolute value of R is less than 1, then, and I write this formula a little different because, okay, if your series starts at 0, then yeah, it's A over 1 minus R. But if your series starts somewhere else, then it's not. So here's the way to do it. It's the starting term, whatever that is. So if the first term of your series is, if the series starts at 2, then it would be AR squared. Starting term divided by 1 minus R. And if your series happens to start at 0, then that very starting term will be A. Okay, this is the result on geometric series. And the proof, I'll tell you, we are gonna talk about it, but I want to give you time to digest first. We write out Sn. Which would be A plus AR squared plus AR cubed. The second to last term is AR to the N minus 1, and the last term is AR to the N. And find a nice formula for Sn by multiplying it, Sn, by the quantity 1 minus R. So if you take this big expression I've just written here, and you multiply on both sides by 1 minus R, on the left-hand side, you'll get 1 minus R times Sn. It's a trick. It's not something obvious. And on the right-hand side, you'll have 1 minus R times this whole thing, which is A plus AR squared. I'm not going to write the cube term. The second to last term is AR to the N minus 1, and the last term is AR to the N. You would then distribute the 1 minus R. And I'll do this for you next time, and you'll see that you do get a nice formula. The thing you get out here when you distribute this only has 2 terms. Most of the terms cancel. And then you'll divide both sides by 1 minus R, and you'll get a nice formula. We can take the limit. We'll come back to this next time. What I'm going to do for you guys right now is I'm going to extend that last homework set through to Wednesday. Right, through to Wednesday, so you can finish it. And then I'm also going to publish a fresh homework set, so those of you who already finished the homework from last week can look at the first few problems from the next homework set, which is going to be more 11.2 stuff and also some 11.3 stuff. We haven't touched 11.3 yet, but 11.2, I think I left out the geometric series stuff from your last homework set. I'll have to take a look, but please take the time to finish the 11.2 homework that is up now. And then if you finish that, take a look and I'll post a new homework set for you guys a little later today. The current homework set that was originally going to be due today will be due on Wednesday instead because we lost last Friday to homecoming. And we will pick it up here next time. Alrighty. Alrighty. I'm going to go ahead and turn off the share here. And let's see. One or two little more things to handle here that I'm going to handle in the chat. If you guys are done, you're welcome to leave. I just got one or two people I need to talk to real quick. All right, it's just us now, so we can talk outside chat if we want. Any preference between Wednesday or Thursday?
No, I mean, can I do Thursday? I just got really worried when you were talking about the average for the test.
Yeah, it's true. It's true that the class did not do great on this, so definitely take the time to work the study guide problems. If you can bring any of those study guide problems that you're having a difficult time with by office hours on today or on Wednesday, we can talk through them, and I think that would be a big help.
Yes, sir. I will. I mean, I've been working on it nonstop for the test and
Good.
yeah.
All right, man, hang in there. You've had a little extra time to prepare, but I understand things have also been difficult. So don't panic, but just do your best, work the study guide problems and bring them by office hours so we can talk. I think, like I said, that will be a big help. And we'll move forward from here. It's going to be all right.
Okay. Thank you so much, sir.
Of course, man. Of course. Take care.
Thank you. You too.
Bye.